So let us resume the morning session. The next speaker is Riccardo Zecchina, and he will speak about stochastic learning processes and effective energy landscape in deep neural networks. Thank you.
Thank you. Hello, everybody. So I will give a talk which discusses some of the work that we've been doing in Milan in the last few years. And the link with Sergio are these two guys who have been students and collaborators of Sergio. And in general, the environment in Milan is highly connected with Sergio. And this is our group, current group in Milan. And I'm sure you can recognize a lot of people here, Carlo Baldassi, Marc Mesard, then some Luca Saglietti, Rosalba Pacelli, Clarissa Lauditi, Brandon Annesi, and so on. Okay, so the idea today is just to review what we have been doing many years ago on neural network and see what we have missed and discuss what can be done in the next future to understand some open challenges. And the scope of the talk is just to give you some ideas about the physics behind these systems, okay? For those, and I assume that you have not been working in the field. So in the 90s, what we have been doing is to study neural network using the techniques of spin glass theory. So essentially, the idea is that instead of studying the SK model, we use the same technique to study, say, an attractor neural network, which is just like a disordered system in which you plant some attractor that correspond to memories. So you choose the couplings Jij in such a way that certain states become attractor, and you can. So it was a very important result of the 80s to show that you can in fact store an extensive number of attractors as ground state of a spin glass model, and so the model is exactly has the same, that kind of Hamiltonian with the appropriate couplings. And then it has been applied to study so-called feed-forward networks, in which you essentially choose the coupling of a classifier. So you have an object that, given an input, produces an output, and then what you want to do is to find the coupling such that this object implements a given input-output function on a set of data. And again, the tools of statistical mechanics have been used to study this kind of the system very successfully. And the techniques have been the replica method, the cavity method, and a lot of numerical experiments. And I will not discuss this in detail, but just as an historical remark. More recently, say in the last 20 years, the activity has been focused more on the algorithmic aspects of these techniques, in the sense that this kind of methods can be turned into actual algorithm for solving this kind of problem. And this has opened a lot of application and also a new way of using statistical mechanics. And so there's a lot of work going on. There's been a lot of work going on in applying this kind of technique to study not only neural network, but in general optimization problem. And I think you heard a talk by Andrea Montanari at the beginning, yesterday morning, about one of the latest algorithms in this line of work. So all these techniques have had a lot of impact in learning theory, in constraint satisfaction problems. It has been used in error correcting codes, and then application in a lot of interdisciplinary application. I think that, for instance, in the context of protein contact prediction, the use of belief propagation, which is nothing but the algorithmic version of the cavity method, was probably the first technique that has been used to infer contact from sequence data efficiently. Then, things evolved, but it was kind of a breakthrough at the time. Okay, so given this scenario, what happened? It happened historically that, again, in the 80s, 90s, when I was a student, there was a lot of activity, excitement, and so on and so forth. And then, all of a sudden, the research activity in neural networks died out. there was a so-called winter of this kind of research. And in this period, our community started to study optimization problems rather than machine learning problems. So this was say, a dark period for machine learning around the year 2000. So at that time, what we did is to develop the tools by kind of studying, instead of just learning problems, optimization problems. And then all of a sudden, there's been this so-called deep learning revolution, which mainly empirically, people have observed that the neural networks can be trained to perform unprecedented, say, predictions, and so everything has changed, and deep learning is used across fields now as an extra tool to do research. Also, deep networks are kind of an ideal object for statistical mechanics, because this is the size of the network as time increases, and it's kind of impressive because in few years the size of this network has reached numbers of the order of hundreds of billions parameters. So we are really in the thermodynamic limit. So today, if you use a natural language processing device, the most advanced one, it has 200 billion parameters that you have to tune. So these are just like spins that you have to find the configuration of spins that optimizes this the performance. And so kind of looks like promising for us. So this is the plan of the talk. Probably the plan of the talk is to try to illustrate which is the analog of the energy landscape for this problem, because as we will see, training amounts at minimizing a cost function that measures the number of errors. So it's just an energy minimization problem. And then I would like to, so we've been working a lot about the role of rare states in this landscape, because the main point is that algorithms typically do not satisfy detail balance, and they address states which are not those that dominate the Gibbs measure. That's the key point. So it opens a totally new perspective on the physics of this kind of devices. And so we have a lot of new results that will appear in the occasion of the Sergio's 71st birthday. Not today. Today is just an introduction for next year. Okay. So one thing that, I don't know if there's a slide. No, there's no slide, but yes, here I forgot to say something, is, given all this work that has been done in the 90s, why did we miss the deep learning revolution? Why didn't we predict this kind of, there's something wrong. Okay, it's true that we didn't have enough computational power. It's true that we didn't have enough data. Maybe we didn't have the right theory. This is what, and I think that is the case. So our theory was incomplete. And it was incomplete, let me anticipate, but just because we were obsessed by looking at the equilibrium states instead of looking at the whole large picture of also rare events, which become the relevant ones for algorithms that have nothing to do with detail balance, which do not need to equilibrate. Okay, so so what is the general scenario here? The general scenario is that training neural networks is a highly non-convex optimization problem. So it's just like a physical system with a lot of local minima in very high dimensions, with an exponential number of local minima. And yet, what happens is that the algorithms which are used that are not Markov chains, okay, that satisfy detail balance, not at all. If you use them, they don't work. They are very efficient in finding very useful minima that have very good generalization properties. And another, so this is the first challenge. How is that possible? You know? We have this scenario, and the second challenge is that these systems, in spite of the fact that they have a huge number of parameters, they do not overfit. So again, it's kind of, to me, this is very exciting and surprising because, again, how can you imagine to have a network or a system that has 200 billion parameters, that fits data, fits also the noise, and yet it doesn't overfit? if you have you want to fit points with a polynomial of degree 200 billions, I guess you would imagine that this is going to fluctuate a lot as soon as you go out of the domain in which but this actually turns out not to be the case. So there's some interesting stuff going on. So let me just fix the model. So we are going to study models of this form. So essentially, so we're not going to study attractor networks, just feed-forward networks. So you have data enter on the left and go out on the right. And in the nodes, you have some nonlinear function that is implemented. So each node implements a nonlinear function of the weighted sum of all the input that reach the node. Okay, so well, each node implements that function. So overall, the function implemented by this architecture is just, you know, a concatenated function, you know, just represented by the architecture. It's a composite function. So it's, in principle, it's very complicated. Each node is nonlinear. So you see, it's a highly complicated object to optimize. And and the idea is that we want to find the connector, the weights, the couplings of each layer in such a way that on a given training set, this network implements the right input-output function. So if you have images, the network is capable of associating to a certain image the correct label for all the images in the training set. And then at the end, you cross your fingers and hope that this is going to generalize well to images that the network has not seen yet, that do not belong to the training set. So this is the general framework. So what you want to do is to, so this is the true energy function is the so-called error loss. So essentially you want to minimize the number of errors that the network makes on the examples. That's it. It's very clean and simple. So this is the true energy function. So you have a system and you want to minimize. This is actually what this is what you have access to. Because you have the training set, so you know which are the labels, so you can measure this energy. And so you would like to know, how does this energy change as you change the couplings in the system? This is your problem. And then you want to find those minima that minimize this energy function, which also have good properties, generalization properties, namely that behave nicely when you present new patterns. Now, the drawback of this energy function is that is not differentiable, which means that you cannot use gradient-like algorithm to search for the minima. So what people have been doing is to use other loss functions, like just the mean square error or the cross entropy functions. So, okay, these deltas here are just essentially the output of your function of the network. It's not very important to enter in the details unless you're interested in. But essentially, instead of using that error function, you use some surrogate loss functions, such that you can actually differentiate them with respect to the parameters and then choose your stochastic gradient process in order to find the minima. And this is what has been going on. And what is surprising is that by using this, in particular this function here, this very complicated optimization problem becomes often easy to solve. And this is not at all obvious. So, so the general idea that we've been, since the 90s, that we've been looking for is just to consider the error loss function just as an energy function, then you do the statistical mechanics of that. So you construct your Gibbs measure, and then by changing the temperature, you study different energy levels, okay? So the idea is that you want to go at 0 temperature and see which are the minima of this function, because you want to minimize the number of errors in the training set. So you want to minimize the energy. So just to be, I mean, this energy function at the end of the day is nothing but a complicated spin glass, okay, in terms of physical model, with long-range interactions, of course. And so this has been the scenario that has been developed. And so, as I mentioned in the beginning, this has been applied to some simple systems, and a lot of interesting results were obtained, like, for instance, you can study how many random patterns you can learn with a network. Right? So because you study, as the number of examples increases, you study which is the minimum of the energy. As soon as this minimum becomes greater than 0, it means that the network is no longer capable of learning patterns because it starts to make mistakes, and that defines the capacity of the network. These kind of questions have been analyzed in the 90s. The point here is, and this is what we have been looking at in the last years, and this is something that we overlooked in the 90s, is that while the dominating, the minima that dominating Gibbs measure can be kind of very sharp and can be, say, in an exponential number, so they dominate the measure, it may be the case that there exist rare minima that are actually those that are targeted by the algorithms that do not satisfy detail balance. And this was motivated by some empirical evidence, because we, as we will see in a minute. So when you do this kind of approach, essentially you tend to overlook this kind of states, and this is the problem. I mean, there are analogies with quantum systems, right? And so the idea is to study essentially what we've been doing, to study the connection between the structure, the geometrical structure of the landscape and the convergence properties of the algorithm by taking into account not only the dominating states, but the subdominant ones, okay? And now what we're going to do to review here is the results that concern, say, good old-fashioned neural network, those that have been studied in the 90s, and the modern ones, which are these highly over-parameterized networks, these networks that contain billions and billions of parameters. So these are two different classes of models. And I'll just review quickly the results for both and see where the differences are and so on. Okay, so good old-fashioned models are, let's take the simplest possible device that is non-convex. So the simplest neural network is the so-called perceptron. It's just one neuron. So a neuron just, it's a linear threshold node. So you take the sum of all the weighted sum of all the inputs, and then you look at the sign and you decide whether the output is plus or minus 1. That's the perceptron. Now, if the weights are continuous, this device is a convex device, meaning that minimizing the number of errors amounts at finding the minimum in a convex space, and so it's very easy to train. And there's a proof of convergence, everything works out fine. But these are not but this kind of device has a lot of limitation in terms of computational power, so you need to go non-convex. And the simplest non-convex device is just a network in which the weights are discrete. Already the fact of having discrete weights makes things completely different. Or you need to have more than one layer with continuous weights. That's the idea. So the simplest non-convex devices are either multi-layer network with one hidden layer at least with continuous weights, or it can be even just one single neuron with discrete weights. These are the two. And the simplest object to study is, in fact, the case in which you have discrete weights. And this is also simplifies life because you don't have to take into account the norm of the weights. So it's kind of a simpler setting. It's just like using spins, discrete spins plus or minus 1 rather than continuous spins. Okay, so what we are going to do is to study the simplest device, which is not even this architecture, it's just one node that implements just a sine input-output function. And the energy function will be just counts how many errors you're making. So given a training set, given a set of examples, so some input vectors and some corresponding labels, you want to find the weights W such that the output of the network coincides with the desired one. You count how many mistakes you make, and that's your energy function, okay? And we're going to consider the case of binary couplings. And we are going to feed to this network a number of examples which is proportional to the number of degrees of freedom. That's the setup. I hope it's clear. And this model was solved exactly, well, in '89 by Marc Mézard and other people. And essentially what you have for this model is the following scenario. As you increase the number of patterns, the entropy of the ground state, so the log of the number of configuration, the typical, that are able to store, so that have zero energy, namely they make no mistakes, as a phase transition as alpha equal 0.83, meaning that if you try to store in this device more than 0.83n patterns, you start to make mistakes. That was the idea. And so this, by the way, is kind of very similar to a random energy model in terms of physics, because it has, if you take alpha greater than this alpha critical, it has a freezing phenomenon, which is similar to the Derrida's random energy model. But having said this, if you look at the geometry of this ground state, you can show that the geometry is, okay, I think the picture is better in the other case, is the following. So there are an exponential number of ground states, of zero energy ground states. So this curve here is the entropy and goes to zero at the critical point. And what you can show is that the distance, the typical distance between solutions is of order n in Hamming distance. So which means that it's a pure golf course. So the size of these dots, it goes as the square root of n. So when you divide by n, it means that these are point-like. You have this kind of, and you have always a distance that separates the points, which is of order n at the dominant level. Okay, so these are the typical, this is the typical geometry. And you can actually show this by computing explicitly the typical distance between solutions using the Franz-Parisi approach. And you can show that for any value of the loading parameters, for any, as soon as you start to feed the number of patterns, which is of order n, it becomes extensive, the distance. So everything is far apart. And in fact, if you run a Monte Carlo algorithm on this problem, you get stuck. And if you increase the size, there's a very old paper by Horner, you can show even analytically that you get stuck and you don't move from random initial condition. You can never load the energy of this system when the n goes to infinity. For finite values, what happens is you get a plateau, but as soon as you increase n, this plateau goes up and becomes longer. And at the end, so essentially, it's impossible to find ground states for large n. So this was our initial motivation, because this is embarrassing. So you have a very simple neuron with discrete synapses, discrete weights that are called synapses in computational neuroscience, which is pretty realistic, because it's more realistic to think that a synapse is discrete rather than continuous, because it has a finite number of levels. And apparently this object doesn't work at all. So, however, there's, there was numerical evidence, this around 2004 or 5, I don't remember exactly. So we designed an algorithm which could very quickly find solutions. So there's something wrong going on here. And what was going on is that, in fact, this scenario is incomplete. It's absolutely true that finding this isolated solution is impossible. I mean, it's very, very hard. I mean, only for finite n you can find them. But this is not the end of the story. There are other states which are not described by the direct replica calculation, that are rare events in terms of deep measure, which are those that are found by the algorithm. So you see, the theory for this kind of network is not a theory about the dominant states, but it's a theory about the subdominant ones. That's the basic idea. So, and in fact, as we designed, I'll tell you how in a minute, but we designed a Monte Carlo process which actually targets these rare states, and it actually it's extremely efficient in finding ground states. So this was a proof, a constructive proof that everything was correct. I have to keep track of the timing, I hope. And so the idea that we developed together in Milan is the following, is that instead of looking for ground state, the large deviation study that we implemented is based on the following idea. Instead of looking for just configuration that minimize the energy, we are looking for high dimensional spheres, so hyperspheres of radius, of extensive radius, and count how many solutions are inside these spheres. And we use this, take the log, and we use this entropy as an energy function. So instead of looking for single ground states, we look for regions that have a very high zero energy states inside. Okay, that's the idea. And if the situation was this one, then clearly, if you take a sphere that surrounds one point, then that function would be completely trivial, because it would be the log of 1, which would give 0. So at the beginning, when we did this calculation, it was not totally obvious that it could have been just a waste of time, right? But we had numerical evidence supporting this, so we were kind of hoping. And in fact, so now if you introduce this local entropy function, which is just minus the log of the number of configuration within a hypersphere of radius d with respect to a centroid, a center w tilde, w's are the analog, the dynamical variables, you can try to search in the space of W for these spheres that are particularly entropic, okay? And this is, you know, as it will turn out, this is a large deviation approach because the kind of regions that we will find are not those that dominate the measure, okay? And so, well, let me be quick. So now if we apply this kind of analysis to the simplest non-convex network, what we find is that, in fact, up to value of alpha, which is 0.77, which is very close to the critical capacity, there exist regions that were totally missing from the equilibrium analysis that are very dense in solutions. So, for instance, in this plot, you see here is the distance from the center of the hypersphere, and this is the entropy. And notice that this curve here is the upper bound, it's just the binomial coefficient. So it's the highest possible entropy you can get inside the spheres of radius d. And you see that for small distances, these spheres are really extremely dense. So it's like having a golf course with lakes that are super dense. And these are the kind of states that are targeted by the algorithms. One can see this empirically, and so this was, so we have a prediction of also when algorithms start to fail, and so this is something that we have to do, but this has a nice, I think this is a conjecture, but I'm ready to bet on this, and we just have to do some calculation, but Carlo Lucibello is too lazy to do things, and so there's a results from some mathematician working on computational complexity, and they've studied a particular version of this model, and they conjecture that there exists a value of alpha, of these loading parameters, above which all stable algorithms are going to fail. A stable algorithm is an algorithm such that if you perturb the initial condition a little bit, it's kind of smooth, okay, with respect to this perturbation. So they have a very precise prediction, and I'm pretty sure that we're going to find the same consistent results. Actually, this is a rigorous formulation of all the results coming from statistical physics. But now we are going back. So Carlo is very brilliant. I was just teasing him a little bit. So the question is, one question that we have been looking is, you know, these states, how do they really look like? So how is it that we miss them? In principle, when you do a replica calculation, you can actually tune, this is for those of you who are expert, but you can use the so-called Parisi parameter to look also to subdominant states. But even by doing that, you miss this kind of states. So there's something in the definition that it has to be clarified. So in order to address this problem, we have recently analyzed the structure of these lakes, of these dense regions, by looking to solutions that have that are particularly robust. So not only you want your network to give the correct output, but you want your network to give the correct output with a robust margin, okay? So that's the idea. So you look for particularly robust solutions. So you impose a margin with respect to the separating hyperplane. And then you start, and so you would like to see if these dense regions contain a lot of this high margin solution, because at the end, clearly high margin solutions are very dense in solution because the classification is just given by the output of the function, and you are imposing an extra margin. So if you find solution with the margin clearly around you, you will have a lot of solution with smaller margin, okay? So we started to analyze this problem, and the first observation that we actually already had in the 90s, but we just didn't look at it, is that if you look at all the ground state of this neural network, so the typical ones are at a given distance. But now, if you look at, you measure the typical distance between solutions that have a certain margin. The typical distance, so here's the margin, this is the distance between typical solution with a given margin. So zero margin, you have this, this kind of distance, but if you impose a certain margin, then the distance goes down, which means that if you look at solutions which have a large margin, they tend to coalesce. There's an aggregation phenomena. This, they're still exponentially, there's an exponential number of them, but they are close by. So they kind of tend to attract each other, which makes sense. You flatten the surface and you know, there's a flatter valley and you have more lakes in that valley. That's more or less the idea. But at the time, you know, many years ago, we didn't consider this problem. And, and so then what you can show is that, in fact, these highly robust solutions are surrounded by an exponential number of solutions which have a smaller margins, so that are the ground state without robustness. And so somehow you can imagine that these ground states are composed of very high margin solutions which are connected to each other by solutions that have a smaller margin. So if you, for each value of the margin, you have states in the physical sense, if you constrain your Hamiltonian to have that kind of margin. But in order to understand how they are connected, you have to consider all possible, say, Hamiltonians with the different margins. And so only if you take this view and try to see how the different kind of states are connected, you understand that they form a cluster. This is why we missed somehow the original version. Okay, these graphs might not tell you much, but essentially what these graphs are telling you is that if you have low margin solution, what happens is that they tend to be isolated, and if you have high margin solutions, they tend to be surrounded by solution of smaller margin. Okay, so these are the curves, the entropy versus distance, and here you have the number of solutions with the smaller margin. So you see, for small k, you have a non-monotonic behavior, and otherwise monotonic, and then you have numerical checks. So at the end, this is the scenario. Sorry for the scenario is that you have these are the dominant solutions, the typical solutions, but then there are atypical solutions that tend to aggregate, and they become connected through solutions that have a smaller margin. So this is the scenario. It's a very fluid scenario. Okay, well, let me skip this because I guess there's no time. And what is interesting is that the same result has been proven rigorously by mathematicians last year. And what I find funny about these two pictures is that they represent the same object. So that's the view of mathematicians. There's a two-dimensional version of this state from mathematician, and this is our view. And I think the mathematicians are more correct than us, but okay. These are not real pictures because we are in high dimension, just kind of idea. But this is just to say that everything has been proven rigorously. So things are becoming much faster. Now, I don't know how much time I have because, wow, that's bad. Anyhow, so somehow, as I told you at the beginning, in order to implement algorithm, you cannot use the error loss function. So the engineers use other loss functions, which can be mean square error, cross entropy, and so on. In particular, say cross entropy, it interprets the output of the network not as a label, but as a probability of the label, and then you implement a maximum likelihood approach, and so you can define a maximum likelihood cost function. It's not very important. The important thing is that everything is somehow equivalent to look for robust kind of solutions. So this is just to say that by using this kind of loss function, you tend to convexify a little bit the landscape. You are going to essentially lose track of all the narrow minima because you are this loss function impose a sort of robustness in the size of this minima, and they tend to focus on the right ones. But the key point is that if you from the beginning you start by using this loss function here, you lose track of the physics. You don't understand anything because you only see what your algorithm is going to tell you about the problem. You don't really see what is happening. You lose track of all the geometrical structure and so on. And you can only use this kind of loss function if these minima that are flat are present. Okay, so somehow it's part of the algorithm, and I think this explains quite a bit why it's difficult to discuss also with the machine learning community, because somehow they just look at the algorithms, and they have, along the years, they have developed sophisticated algorithms, but they are just looking at the problem from a very narrow perspective. Okay, since I don't have time, I'm going to skip all this part. And let me just tell you one thing, which is, if we take a finite temperature version of our entropic model in which we look for these spheres, everything can be turned into algorithms. Okay, so it's not just a theory about the typical behavior of the system. We can actually design algorithms. So these are all algorithms that have been derived by this approach, and in particular, this entropy stochastic gradient descent has been used a lot in the machine learning community. It also has a nice connection with quantum annealing, because I don't have time to discuss today, but essentially one can show that it's very the kind of sampling that quantum annealing is doing on this problem is strictly related to sampling this out of equilibrium states. So the conclusion for this good old-fashioned model is that the learning landscape is glassy. However, the existence of this rare wide minima allows algorithm to work, and this wide minima arise from the coalescence of these high margin solutions, which are connected by a solution of lower margin. So it's this kind of fluid scenario. Now, when you go to over-parameterized models, meaning networks that have much more parameters than examples, what the typical line of thought of research in machine learning is to think that all the local minima, all the narrow minima disappear, and only the wide minima remain. And so they think that the volume associated to this wide minima becomes the dominant one. Okay, this is and then we are going to have to understand in this context, as I said before, the problem of optimizing, finding ground state of very complicated nonlinear functions, and also we have to deal with the problem that this system need not to overfit, in spite of the fact that they have a lot of parameters. Just for those of you who are not in the field, the fact of having a lot of parameters is useful because convergence becomes easier. It's easier to train this model. But on the other hand, you have to be careful not to overfit. So it's a very fundamental problem. And okay, since I have a few minutes, let me just mention that according to, say, statistical learning theory, the current models of deep networks should not work. Okay, because we are in an over-parameterized regime, we should overfit. That's the basic idea, unless you regularize somehow the system. Okay, this is a technical part. Just to say that all these kind of models were not used in the 90s because both the statistical learning theory was predicting the failure of this model. I mean, was not concerned with this regime. Let's say, I'm not saying that the theory is wrong. It applies, of course, to the system that they are studying, but somehow that was the idea. This system should overfit. And we also did the same mistake. We were looking to the dominant state of the Gibbs measure. This is what was missing from a theoretical perspective. But then, you know, now we have seen that you can actually increase the size of the system and still perform very well. It becomes easy to train, and they do not overfit. So there's this very famous double descent curve. So if you have a system, a learning device, and when the number of parameters becomes of the order of the number of patterns you want to recognize, you have this peak in the error, in the prediction error, in the generalization error. But then if you increase your the size, it goes down again. It is as if you are fitting data with a polynomial of high degree, and at the beginning you start to oscillate, and your prediction becomes worse and worse. But if you continue increasing the degree, at a certain point, it regularizes, and it starts to oscillate less and rather fit very, very precisely the data without big oscillations. Okay, so let me skip and go to our. So how do we study this problem of overparameterization? We use a model which is called the random feature model. So we start from data in dimension D. We make a random projection in a higher dimensional space. And then we apply into this higher dimensional space a non-convex classifier. That's the idea. So let me, since I have very few minutes, let me go directly to, this is the idea. So we start from dimension D, we have a random projection, we apply a classifier here. Now, what is the point is that we generate data in D dimension, but we project them in N dimension. And so we can, by changing N, we can play with the overparameterization. We can study the effect of having more parameters than data points, and everything can be done analytically. I'm going to infinite limited. There's been a lot of results by different groups showing how this model can be analyzed. Okay, these are some papers about the double descent curve, and then this kind of sorry, I have the reference. I missed them. Okay, here you have yeah. So here you have some paper from physicists about this this model, even though in the convex case. But so and what we found to conclude to close up is the following: is this kind of diagram. Let me try to explain. So here you have essentially a parameter measuring how many patterns you provide to the system. So sorry, this is this parameter alpha is the ratio between the number of patterns and the number of variables, how you overparameterize the system. So if you lower these parameters, you're going to increase the size of the system. And on this axis, you measure how many examples you give to the system with respect to the dimension, to the additional dimension D. So this is, say, a measure of the amount of information you're giving, and this is an inverse measure of the size of the system. And so what happens is that you move along this curve here, and in this system, you can show that what happens is that at the beginning, you are in a phase in which you cannot fit your data because you do not have enough parameters. At a certain point, you reach a phase boundary in which you start to be able to fit the data in principle by doing the statistical mechanics. I'm talking about random patterns here. So you start to have some minima that are point-like, but then there is a second phase transition in which these rare events appear, these rare minima appear. And this is the phase transition where the algorithm starts to find solution. Here it's difficult to appreciate because it's 1 over n, but anyhow, so there's a first threshold in which solutions start to appear, and the second threshold in which you can actually start to find solution. And what you can show is that the effective loss functions that people use for training are actually targeting this kind of minima. Okay, and what is interesting to show is that in this highly overparameterized regime, you still have a lot of narrow minima that have, let me say, bad generalization properties. So you can show that they exist. So this idea that narrow minima disappear is wrong, and not only is wrong, they still dominate the Gibbs measure. But at the same time, you have these rare states that become larger, and they have very good, close to base optimal generalization capabilities. Okay, now we are trying to, and I mean, this has been checked numerically by some very expensive, really expensive experiments at Google, in which they have trained 10,000 different models, I don't even remember. And they have checked that flatness is actually correlates with generalization. So this is theoretically an open problem, but it's kind of quite accepted. And so this is the scenario that we found. And so let me conclude because I'm out of time. We are now working on many different aspects. We are applying this to different models, like say, jamming problems, associative memories. And in general, this idea of having these wide minima allows to design very effective algorithms that are simple. And from a theoretical perspective is, I think, this points to the fact that in order to study the physics of these problems, we really need to study the out of equilibrium properties. Either because we are going to study certain type of algorithms, so we want to know how they converge, or if you want to have a static approach, which is the only one we can really deal with, you have to look to the full geometrical picture and look to this rare states, which are particularly entropic and which we missed in the 90s. And so this, I think, was one of the components. And now, so we have already seen that this has led to many algorithms. And I kind of, for next year, I hope to that we have another occasion like this. And we're going to apply these ideas to some constructive models. Okay, thank you.
Thank you very much for this nice talk. Are there questions?
Thank you. Well, in a sense, I'm asking you the impossible task of making me a summary of 20 years of cavity method, but maybe a selected question that I would like to make is if this new understanding of the landscape that sometimes happens in some models can be tested in a special model that I like, which is number partitioning, which is really simple and really REM-like. Does number partitioning have this landscape, or it is really REM-like?
This actually, I was studying this problem probably 3 weeks ago. Really, I was asking exactly the same question. But the problem with number partition, I mean, this is a very technical discussion between two of us. But the number partitioning problem, I don't know if it is clear. You have numbers, you want to separate in 2 sets such that the sum of the number in these 2 subsets are equal. Okay, so this is a problem that, depending on the precision of the number, at a certain point undergoes a phase transition. So it's very hard to solve in practice. The point is that for the number partitioning is, first of all, the minima have huge range of fluctuation in energy, and they are narrow. So, I mean, this technique works for systems which have these rare states. It doesn't need to work for all the systems. For instance, if you take error correcting codes, which are optimization problems that by construction are such that all the ground states are isolated, it's totally useless to use this approach. So you need to have problems in which you want to look for that have to have this kind of property. And neural networks are exactly that kind of systems. So the idea was, you know, it's rather than, of course, it would be interesting to apply this. Actually, Federico Ricci and co-workers have applied this to some graph bicoloring problem, and they were able to find ground states where Monte Carlo algorithm fails and so on. But in general, if you do have these ground states, there exists an heuristic algorithm that is going to find them. So then the fact that number partition is hard is a signal that that's not the case.
Other questions?
Thanks for the talk. There is a thing that maybe has been said, but maybe I missed it. So if I understood correctly, the reason why sampling the Gibbs measure doesn't work is because it gets these narrow minima, which are the dominant one. But instead, if I do back propagation or this other algorithm, they get to the coalesced. Is there a general picture of how these other algorithms are capable of seeing what the Monte Carlo is not able to? Yeah, well, there's nothing rigorous about this, because it's not because I cannot give the argument. Nobody can give the argument. Yeah? But the 2 main reasons. One is that they use surrogate loss functions, which just don't see all the traps by definition. Okay, and so they just, for instance, the cross entropy. I mean, to be a bit brutal, imagine, so the cross entropy interprets the output as a probability, but there's nothing stochastic in your system. It's fully deterministic. So for some reason, you get to take the output and then you flip a coin, but that doesn't, you know, make real sense. What they're really doing is to modify the cost function in such a way that they only see this kind of minima if they exist, and it is suboptimal. That's one thing. So the surrogate loss function have this, and also they use plenty of regularization techniques. So the algorithms are that you always inject noise in the system, so you don't see again, for this reason, the narrow minima. Then initialization is super important. So they use appropriate initialization that are in some sense closer to this kind of states, and so on.
So it's an evolutionary process that has been going on for 10 years. And in fact, it's very, very difficult to distill all the aspect, but that's the main reason. So they modify the problem in such a way that what remains is only this.
Just a quick question. With Federico Ricci and another student, we studied the tricks or SAT problem, both from with the classical algorithm, with the quantum annealing. And we found that the quantum annealing followed, in some sense, the classical algorithm, in the sense that got stuck because of entropy barriers. Is it similar to what you were hinting at, the difficulties that quantum annealing has? This phenomenon, or?
I don't know exactly. I can't remember the work on SAT, on the SAT problem. But what I can actually, I mean, I even have the slides here for some reason, but I don't think I have time. So we can discuss. But so what happens if you apply quantum annealing to this kind of system? It's again trying to be brutal here. What you're going to do is you take your energy function, and that's going to be the Z component of your Hamiltonian, right? And then you add a transfer field, and and then you apply Trotter's transformation, and you can show analytically that the Trotterized formula, so in which you have many replicas of your system which are coupled by a term, is very similar to the expression you have for this local entropy Hamiltonian. And in fact, what quantum annealing, it works very well for this kind of problems. So what is the idea? The idea, in my opinion, is the following: is that as you introduce the transverse field, you have a dynamic term in the Hamiltonian, which is absent in the classical case. And the fact that you have a wide minimum allows the wave function to delocalize. Somehow you encode in the energy this entropic information. And in fact, that's exactly what happens. So somehow you do not have to think to the efficiency of quantum annealing because it tunnels between narrow minima. No, that's not the point. You need to have this wide regions such that the wave function can delocalize, and so you can gain energy from delocalization and minimize that energy. So it's very interesting, in my opinion. So that's so I don't know actually how it applies to.
It's actually similar to what we found, but for us it's a problem because since there is only a single minimum which is well isolated, the fact
because you're studying a planted because you're studying a planted problem. Yes, sorry, I missed that. Yeah.
Yes.
Okay.
Okay, let us thank the speaker again.